Okay. See if we can get this going. There we go. All right, cool. So this is the review video, I suppose, for our topic one mid-quiz review. And you can see how it all works together. All right, okay. So let's dive in. There's only going to be 6 questions on it. So what is the difference between a rational number and an irrational number? So a rational number can be turned into a fraction. So for instance, just a real quick rundown of examples of that, right? You can take a regular number like 7, you can turn that into a fraction like that. You could take a decimal like 0.1. This could be turned to 1/10. You could take a repeating decimal and turn that, right? There's a whole slew of work that we've done on that, but the shortcut for these particular types of problems is you basically just put it over 9. Okay, so you can take a regular number, a whole number, make it into a fraction. You can make an integer like a negative number, put it into a fraction. You could take a decimal, put it into a fraction. You could take a repeating decimal, turn it into a fraction. So those are rational numbers. It comes from the word ratio. Ratio is just a word. Okay, now irrational numbers. Cannot be turned into a fraction. That's the big difference. Okay. So whereas all your rational numbers can be turned into fractions, your irrational numbers cannot be turned into fractions. So what this means is the technical word is non-terminating. They basically never end, right? So they go on forever. And there's no pattern, right? So they don't repeat. A good example of this would be pi. Right? Pi, as far as we know, as humans, goes on forever, and there's no pattern that you can use to turn it into a fraction. So that's the idea. So what is the difference between a rational number and an irrational number? A rational number can be turned into a fraction. An irrational number cannot be turned into a fraction. Okay. All right, now we're going to take this 0.2 and then 3 repeating, convert it into a fraction. First step, set it equal to x, and then we have one repeating decimal. So we take 10 to the power of that one repeating decimal. That's going to be 10. So then we take that 10 and we multiply it on both sides. Okay, 10 times x is 10x. I'm going to leave a little space right here. Now this 10, what happens, all it does is really it moves the decimal place over, right? So it's going to be 2.3 repeating, okay? And then now we got to get rid of this repeating decimal. So what we're going to do is we're going to subtract this x on the left side, and we're going to subtract this 0.23 on the right side, okay? Now 10x minus this x is 9x, and then the 2.3 repeating, we will do 2.33 repeating, kind of just extend one decimal out, because again, it goes on forever, right? And we're going to subtract 0.23 from it, okay? Gets rid of the repeating decimals. 3 minus 2 is 1. Bring that 2 down, so that becomes 2.1. We're in that room there, but 9x equals 2.1. Okay, now we want to get our x by itself, so we divide by 9 on both sides. We end up with 2.1 over 9. Sorry, early. And then we can't, in our answer, we can't have a decimal and a fraction combined. So to get rid of that decimal, kind of just like we did up here to move that decimal, we're going to multiply by 10 on the top and the bottom. It moves the decimal over here, so it becomes 21 over 90. And then we got to figure out what we can divide the top and the bottom by to simplify the fraction, if we can simplify the fraction. Numbers that go into 21 are 1 and 21. Those aren't going to help us, but 3 and 7 also go into 21, right? But 7 doesn't go to 90, but 3 does. So we'll divide by 3 here and here. And so our answer becomes 21 divided by 3 is 7, and 90 divided by 3 is 30. There you go. There you go. Okay, is the square root of 15 greater, less than, or equal to 3? Well, I'm going to take that 15. I'm going to take a look at my list of perfect squares, and I'm going to figure out that it's in between man, it's early. 9 and 16, sorry. Okay, so we know that the answer is between 3 and 4, right? So we can actually kind of like answer the question here, but we're actually going to take it a step farther and estimate the decimal on it, right? We know it's going to be 1 away from 16 and 6 away from 9, so we know it's closer to that 16. We know it's closer to 4. So if we throw that on a number line, 3 and 4, 3.5 is directly in the middle. Since it's closer to this 4, because that 15 is closer to 16, we know it's on the right side of our number line. And it's actually pretty close to 4, right? So I'd say it's like maybe over here even. It's maybe like a 3.8, 3.9. So let's kind of write it out here. We say the square root of 15 is equal to 3.9. So now let's do 3.8. That's probably a little more accurate. So now we can answer the question. Is the square root of 15 greater, less than, or equal to 3? Well, 3.8 is greater than 3. So we would say the square root of 15 is greater than 3. When it says show your work, this is your work to prove that. Okay. Solve the equation x squared equals 12. So to kind of get rid of this 2 on this side and bring it over here, because again, you just want a single x on your left. You have to do the inverse or the opposite of what's currently happening. So squaring something, the inverse of that is square rooting it, right? So the square root and the square go away, leaving your x all by itself. And then this square root of 12, we could do the exact same thing we just did here, but if you got this right, then you've proved that you can do it, right? So we're not necessarily testing that skill on this problem, okay? What we are testing is the fact that this technically has 2 answers, right? And technically this would too, but I'm not worried about it on this one. But I definitely want you to understand that these square roots, unless it's like a word problem where it doesn't make sense to have a negative answer, these will all have a positive and a negative answer. Again, the reason for that is because when you multiply 2 positives together, you get a positive, but you also multiply 2 negatives together, you get a positive. So this is, root 12 times root 12 gets us to 12, but negative root 12 times negative root 12 also gets you to 12. So that's kind of the reasoning behind that. Tanner has a small cube-shaped box. Its volume is 729 cubic centimeters. What is the area of one face of the box? Well, that's your clue right there that you're going to be looking for a cube root. So we're going to cube root 729, just like that. Let's see, that's 9. Okay, so what that means is that we have this cube. Okay, the volume of it, all the space inside, is at 729. This 9 centimeters means that one edge of it is 9. And now if we want to find the area of one face of the box, right, we've gone basically from a 3-dimensional cube to a 1-dimensional edge, and now we're going to a 2-dimensional area. Okay, so area is going to be side length times side length, and since this is a square on the front, right, cube, square, they're all kind of like all the edges are the same measurement. It's one of the properties of them. We know that this is going to be 9 as well. So the area, right, is length times width. So it's 9 times 9. So the area is 81. So what is the area of one face of the box? To summarize, we could say the area of one face, if I could, right, of one face is 81 cubic. No, area. No, I'm right. Centimeters squared, not centimeters cubed. Okay, the area of one face is 81 centimeters squared. Ta-da. Right, 1.2, repeating as a mixed number, show your work. Similar process to what we did for number 2, okay? But the addition here is that we'll have a whole number kind of out front. Now, what I recommend is that you get rid of that whole number and add it on at the end. It makes the math a lot easier, okay? So we're going to have this x equals 0.2 repeating. Again, it's 1 repeating, gosh, can't get that, 1 repeating decimal, so it's 10 to the power of 1 is equal to 10, kind of that same process here. 10 to the power of 1 is 10. So we multiply by 10 on both sides. We get to 10x is equal to 2.2 repeating. Again, it just moves that decimal over. Now we've got to get rid of that repeating decimal. So we subtract x on the left, subtract 0.2 repeating on the right. Okay. 10x minus x is 9x, and then 2.2 repeating minus 0.2 repeating. Those cancel, and we're left with 2. Okay, so 9x equals 2. We divide by 9. We end up with x equals 2/9. Oh shoot, look at that. We even used that as an example up here. Now, you wouldn't get full credit for this one because you're missing the 1, right? So 1 and 2 ninths. That's your answer, and there you go. Ta-ta.